Welcome back to the last two talks of the 11th Annual Pappalardo Symposium. And this talk will move from the previous subject of interfaces now to membranes in a different area of physics by Silviu Pufu.
Thanks for the introduction. So I'll be talking about a membrane puzzle. And throughout this talk, whenever I'm going to say the word membrane, I'm not going to be referring to a membrane in biology. You should think about these membranes as surfaces, like the surface of a drum right here. And this is a puzzle in string theory. So before I can tell you what the puzzle is, I should tell you two quick things about string theory. The first one is that string theory, in addition to strings, as you might have guessed, also contains membranes, which are surfaces on which strings can end. And you should think about these surfaces as some giant sheets of paper hanging out somewhere in the sky, and when they get close together, there would be strings connecting them. So this is a picture of that. It's just a stack of 3 membranes and connected by strings. And each string starts on a membrane and ends on a membrane, and the 2 endpoints of a string need not be on the same membrane. All right? The second quick thing about string theory is that these strings can move. They can move along the membranes. And so essentially they can move in 2 dimensions. And also these strings interact with each other. And now if we think about quantum mechanics, quantum effects can have a dramatic effect. In particular, they can make these strings bind together into completely new objects. And this is not entirely unfamiliar. In our world, this happens. The proton and the neutron are made of quarks, and because of the strong nuclear force, the quarks bind together into protons, and the protons look like nothing like the quarks. So now I can tell you what the puzzle is. So here's a question. Given a stack of n membranes, how many kinds of particles are there that can move in 2 dimensions along the membranes? Well, I just told you that the strings can move in 2 dimensions along the membranes. So let's just count the number of strings, the number of kinds of strings. So now each string needs to start on one of the membranes in the stack and needs to end on one of the n membranes in the stack. So in total, there are n times n equals n squared possibilities. But as these words suggest, this is a little naive because we didn't take into account the interactions of the strings with each other. So in some sense, this is just a classical guess. The question is, what is the quantum answer once we take into account the interactions between the strings? On the next slide, I'll tell you what the quantum answer is, and then I'll tell you it's not going to be n squared, it's going to be something different, and then I'll tell you why that's so puzzling. So how can we figure out the quantum answer? Well, we can figure it out indirectly using a surprising and pretty amazing equivalence, which in itself would deserve its own talk. So far I've been talking about these membranes as having strings stretched between them, and I've been talking about the quantum physics of these strings. However, these membranes are very big. And if they're very big, they must be very massive. And whenever we have really massive objects, they curve space-time. So in particular, they can form a black hole horizon around them. They can form a black hole. And the surprising equivalence is that the quantum physics of the strings connecting the n membranes is equivalent to gravity in the presence of these membranes. And this equivalence is actually also useful because anything that we can compute in terms of the quantum physics of these strings, we can also compute in gravity. And Stephen Hawking taught us how to think about gravity, how to compute things in gravity. In particular, he set out some rules that tell us how to calculate the number of kinds of particles through gravity. And if you use the rule set out by Hawking for a stack of n membranes, the number of kinds of particles goes like n to the 3/2 instead of n squared. I should say that I think about this computation, the first person that comes to mind is Igor Klebanov, who did this in '96, and I'll show you a picture of Igor in a few slides. So now, this n to the 3 halves is not puzzling just because it's not equal to the n squared that I mentioned before, but also for the following reason. And this is actually quite general. In general, when we have n objects, we can describe, we know 2 ways of describing the properties of these n objects. For example, for some properties, it's appropriate to make a list. So we'd be describing that particular property by a vector. And we have 2 examples of that in the standard model of particle physics. For example, flavor, and I hope you remember these guys from Josh's talk. They're $10 each. I like that joke. So these are the electron neutrino, muon neutrino, and the tau neutrino. And there's another example of this in the standard model where we have color. So the quarks, the constituents of the proton and the neutron, come in different colors. They can be red, green, or blue. And I should say that both flavor and colors are just labels. It just so happens we have 3 kinds of things, and you just happen to call them these names, right? But there's another way of describing properties of n objects using a matrix or a table. And there's an example of that in the standard model. And this is how we describe the strong force, or the gluons. And the strong force describes how the different colors interact with each other. And why is a table appropriate in this case? Well, because we have to specify how red interacts with red, how red interacts with green, how red interacts with blue, how green interacts with red, and so on. Right? So now, a vector has n entries. A matrix has n squared entries. But I told you before that the number of kinds of particles for this stack of membranes is n to the 3 halves. So it's got to be something in between a vector and a matrix. And I bet you haven't heard of anything in between that has n to the 3 halves entries. And I should say that this could, if we can find such an object, this would really improve our lives. I mean, in our day-to-day lives, we're used to making lists and tables. What if there's another concept out there that we've been missing out on that has n to the 3 halves entries? So before I go on, I should tell you that in string theory, there's a less mysterious case than the membranes, which is a generalization of the membrane. So the membrane, as I described it, is a 2-dimensional surface. So if we're stuck to this surface, we can move forward, backward, left, and right. But there's a generalization which I'll call 3 branes. And these are 3-dimensional objects. So if you're stuck to this 3 brane, you can move backward, forward, left, right, up, and down, just like in our world. And much of what I said about membranes also works for 3 branes. In particular, there can be strings connecting them, and the quantum physics of strings connecting n3 branes is equivalent to gravity in the presence of these 3 branes. And we can again ask the same question: what's the number of kinds of particles that can move in 3 dimensions in this case? And the naive classical counting, where we're just counting strings, again gives n squared because we haven't changed anything. But this time, however, gravity, using the rule set out by Hawking, the gravity count also gives n squared. So the lesson that I'd like to draw from this slide is that, look, in string theory, we have these other objects, 3 branes, where the classical counting gives n squared, the gravity counting also gives n squared, so there's no mystery. So then, what's going on with the membranes? So there are some possible resolutions. The first one would be, well, Igor Klepanov was wrong when he calculated n to the 3 halves, and here's a picture of Igor. Well, that's unlikely. He was MIT class of '82. Well, another possible resolution. Well, there could be new concepts needed, as I was just talking about on the 2 slides ago. So there could be new concepts that describe n to the 3 halves particles. Well, that could be. I'm not going to rule it out, but we don't know what these concepts are. So the third possible resolution is, well, let's just work with what we have. Let's just work with the old concepts like matrices and or strings, and if we can do a calculation that takes into account all the quantum interactions of these strings, then maybe we'd be able to see n to the 3 halves. But this sounds like a very hard calculation because the quantum interactions are very strong, and it's not obvious how to take them all into account. But I'm telling you this because this actually works. That's what I worked on, and that's what I'll tell you about. So now maybe I should tell you, okay, why should you care about this? Well, I think there are two main reasons. One of them is that string theory is a theory of quantum gravity. And in our own world, we have quantum mechanics and we have gravity. So understanding anything about quantum gravity, these membranes appear in quantum gravity. Understanding anything about quantum gravity, I think that's valuable. And another reason is to explore possible quantum field theories. Our world is described by the standard model of particle physics, which is a three-dimensional quantum field theory. And in condensed matter, people have systems where two-dimensional interactions are relevant. So those would be two-dimensional quantum systems. So this is the reason why this is important. So far I've been talking about, okay, the quantum physics of the strings connecting and three branes. So what is, you can ask the question, okay, what is the quantum physics of the strings describing N3 branes? Is this something esoteric or not? And the answer is no, it's not. It's just a generalization of the strong nuclear force. The strong nuclear force describes interactions between three colors, but now we generalize it to N colors, and we add some extra bells and whistles. But in any case, this is just a generalization of the strong nuclear force. And the strings that I was talking about are really like the gluons. So they're n-squared types of strings. Well, they're n-squared entries in this matrix, so it's only natural to identify these strings as the gluons. And I didn't color these membranes as three branes as red, blue, and green for no reason. All right, so here's a summary table of what I told you so far about these three branes. Well, gravity predicts that the number of kinds of particles is n-squared. The naive classical guess also gives n-squared. The exact quantum answer I haven't told you yet, but it also better be n-squared. And in fact, we should just use these three branes as a test case of our method when we do the full quantum calculation. Okay? Okay, so what's the quantum physics? That was the quantum physics of three branes. Now, what's the quantum physics of membranes? And the answer is it's also a cousin of the strong nuclear force, but now it's in two spatial dimensions as opposed to three spatial dimensions. And again, the strings are like the gluons. And here's a summary table of what I told you so far about the membranes. Gravity predicts now a number of kinds of particles goes like n to the 3/2. The naive classical guess gives n-squared. And the exact quantum answer I haven't told you yet. But as I alluded to, it should equal n to the 3/2. All right, so how do we do this exact, of course, this exact quantum calculation that takes into account the quantum effects exactly is hard. But for three branes, where the answer should be n-squared, it was possible to reduce it to a classic problem that could have been phrased in the 19th century. And that problem is, what is the energy of n electric charges in a quadratic potential? So this is like electrostatics. So of course, if we have only one particle, it's just going to go to the bottom of the potential well. But if we have more particles, they start repelling each other, right? And in this case, it's important that the nature of the force, the interaction forces between these particles turned out to be important. I told you it's like electrostatics, so these are long-range forces. And this sounds like a simple problem, but it's a little subtle, and it was solved by Eugene Wigner, who found that the spread of these particles in the x direction is square root of n. And then the fact that the energy goes as n-squared is not hard to see. If the position of each particle is square root of n, the energy, since the quadratic potential is the position squared, so it's n. And now we have n particles, each with energy n, so we get n-squared. And just as a fun fact about this, Eugene Wigner found that in the limit where the number of particles is very large, the density of these particles can be approximated by a semicircle. All right, so now how about the membrane equations? And this is something that I've been involved in. So we showed that the equations for n membranes could be reduced to a similar problem. And that problem is, what is the energy of n point charges in a potential which is linear at large distances? And again, the range of the forces is very important in this case. In this case, it turns out that they're short-range forces. So what's the solution? Well, the spread of the particles on the x-axis is still square root of n. If you take the limit where number of particles is large, then the density of these particles approaches a triangle as opposed to a semicircle. And it's easy to see, to calculate the energy. Since each particle sits at some position which is square root of n, the potential is linear, so the potential is also, the potential energy for each particle is square root of n. We have n particles, so n times square root of n is just n to the 3/2. So we're happy. All right, so I think I'm out of time. I should conclude. So the puzzle that I was trying to tell you about is, why are there n to the 3/2 kinds of particles for membranes? And the way we approached this problem was to use the old concepts. We didn't invent any new concepts. We used matrices. And we did the full quantum computation. So we essentially reorganized and solved the problem exactly. So this is as far as string theory goes. Now, as far as electrostatics goes, I would say, well, Wigner found the semicircle, but we found a triangle. And there are models that I haven't showed you where we can also find a square or any polygon or parabola, things like that. Perhaps more importantly, the real life lesson that we should learn, I think it's fabulous that we can actually do these exact computations where we take into account quantum mechanics exactly. And I showed you examples where we knew where there were two-dimensional systems with gravity, with the dual gravity description, and we knew the answer from the gravity side. But the same methods can be applied to other systems where we don't know the answer. So I think that's very exciting, and that's what I've been thinking about in the past year or so. And of course, I should end with an open question. The intuition behind this computation is still missing. The intuition would be counting n to the 3/2 objects, but I told you that there's no concept that describes n to the 3/2 objects, so this intuition might actually be missing. I'd like to thank Neil and Jane for the opportunity for me to think about this kind of stuff. Thank you.
Thank you very much, Silviu. Questions? Yes?
Does the classical calculation include self-interaction? Otherwise, the classical estimate would be n times n minus 1. Do you need to include self-interaction to get n squared?
I was implicitly thinking of taking n to be very large, and in that case, the difference between n and n minus 1 is not important.
Let me ask a question of interpretation in this.
Sure.
Particles in a potential, I can see the interaction, the self-interaction energy,
Yes.
Just from the electrostatic energy. Is there a similar, quote-unquote, electrostatic interaction between the strings? So what is the interaction between the strings that is mirrored by the interaction in that potential?
Interaction between the strings. It's hard to tell. Getting from the strings, I mean, I'd like to know the answer to this question. Going from the strings to these particles in a potential, I mean, we used a bunch of tricks. And in those tricks, some of the intuition was lost.
Okay, so it's a mathematical equivalence between the two calculations?
It is a mathematical equivalence, yes, at this point. Maybe there's some intuition behind it, but that would be very interesting to figure out.
Absolutely. Neil.
The question I'm going to ask might trouble a lot of us, but I'm still going to ask. There's nothing new in the sense that string theorists are a challenge for many of us who understand much about physics. Okay? And from my point of view, I've had this before because there were some of your predecessors who I was very, very troubled with, why they are pursuing string theorists, or string theory. So in your case, that's the fundamental question I would love to know. What happened in perhaps the last 10 years, maybe even longer, for you to decide to pursue string theory as opposed to some other field of physics? What inspired you, or what transformed you, or what event happened for you to pursue a subject knowing full well, I think this is true, among other physicists, they're a little bit at a disadvantage in understanding what exactly it is you are studying.
Okay. Well, yeah. Okay. Good. That's a very good question. What happened was this this amazing equality that I was talking about towards the beginning of my talk between quantum systems and gravity. And essentially, gravity in this case, quantum systems in general are hard, but gravity gives us a handle on these particular quantum systems. And what happened was that when I was starting graduate school, well, people started applying these models where we can use gravity to understand quantum systems to real-world systems, like the quark-gluon plasma, the relativistic heavy ion collider. And this is what Paul Chesler talked about 2 years ago. So this idea that using string theory we can learn something about the real world, I mean, I think that's very interesting.
But Neil, isn't it true that in your heart of hearts, you really want to understand quantum gravity, and you've employed the rest of us to try and satisfy that fancy?
That's an understatement. Thank you.
And that's the other aspect of it.
Well, I certainly recognize there has been a fundamental issue for a long time, to trying to marry either relativity with quantum mechanics or gravity with the other three forces. And this has been a challenge for a long, long time. But it's never been clear to me that this is ultimately would be a field that, I guess through what I look at as almost pure mathematics, that you're going to attempt to solve.
Yeah. There are two aspects of it. There's the quantum gravity aspect of it, and there's also this duality between gravity and quantum systems.
Yeah. Krishna.
So there were two big connections in your talk. One was the one you just referred to in answering Neil's question. Then the other one was this leap between a quantum problem of interacting strings and this red balls and a funny potential with funny long or short range interactions, a 19th century style problem.
Yes.
So there was a connection there also.
There was a connection there.
That connection I don't understand at all because I haven't worked on it. So I'd like to ask you that connection. How do you see that as ramifying and applying in other directions?
Well,
other directions beyond what you've used it for so far.
That's a good question. That connection. Okay, so first of all, that connection relied on supersymmetry. So it can be used to say something about any quantum system that's supersymmetric. That's one way. And once we do that, I would think of this as a way of testing other types of approximations. We can compute the full answer using this method, and then we have other tools where we can do some other types of expansions. Right? So and then we can test the validity of other approximations. I think that's...
I'm still very curious about one thing. In 2 dimensions, you get n to the 3 halves. In 3 dimensions, you get n squared. What do you get in 4 dimensions?
Can I answer 5 dimensions?
Oh! We love 5 dimensions here.
5 dimensions, it's n cubed.
5 dimensions, it's n cubed. Wow! We have a series.
In 4 dimensions, the question is not very well defined. But in 5 dimensions, it's n cubed.
I think I better stop while I'm still ahead.
But that's less puzzling, right? Because it's an integer power of n. N to the 3 halves was somewhere in between. Yeah.
String theory certainly creates a lot of fun puzzles. Let's thank Silviu for explaining one of them.